Okay, so as we continue looking at the second derivative and concavity, I want to really focus in a little bit here on the graph and looking at certain points and recognizing what's going on. Okay, now it says here in the diagram shown, we're going to use this example to kind of drive the beginning of this here. In the diagram shown, B and D are stationary points and C is a point of inflection. Complete the table by indicating whether each value is 0, positive, or negative. Okay? So I want you to think about this here. And first of all, these types of things are important in, or show the importance of understanding our vocabulary. And not just a definition, but really understanding the vocabulary, okay? So when you're told that something is a stationary point, you automatically know what? It could be a max-min or a plateau. The derivative of the function is 0. That's right, okay? So here, f prime equals 0. So actually, we could go in here, B and D both. They already put a 0 in for D, but I can put a 0 in for B in this column for f prime. And I don't even have to look at the graph yet. Okay? Then we're told that C is a point of inflection. So we know, what do we know about C? Yeah, the second derivative equals 0. And concavity should be changing there, all right, because it's 0. So at C, this should be 0. Okay? So now let's think about, all right, if we have C as a point of concavity, let's do concavity in green. All right, just by looking at it, okay, the stuff on the left side, the part of the graph to the left of C, how would you describe that? Concave up or down?
Concave up.
Yeah, it's concave up. If you were to draw the tangent lines would be below the function, right? And that indicates it's concave up. Or concave up looks like a cup, right? It's an easy way to remember it. Okay, if it looks like a cup, then that part is concave up. All right. So then to the right of C, it's concave down. Now that's significant because to the left of C, that means the second derivative is what? What's the sign of our second derivative? If it's concave up, the second derivative is positive, negative, or 0? Positive. Okay? It's positive.
Isn't it? Oh, okay. I see what you mean now.
Okay.
What if it's negative? Like what?
If the second derivative is negative, that means our function is? No, second derivative. It's concave down. Okay? All right? And again, you should be able, in most cases, you should be able to recognize concave up and concave down. All right? Concave up looks like a cup. Concave down looks like a frown. All right? Easy way to remember it. All right, so that's our second derivative, in which case we can come over here and say, okay, at what points is our second derivative positive? A and B. Alright, here's A and B, and it's negative then at D and E. Okay? So there you have stuff with the second derivative. Okay? Now we were told B and D are stationary points. Let's do the first derivative stuff in blue. Okay? If B and D are stationary points, C was a point of inflection. You guys know from what we looked at and what you had to quiz over, we have 3 different intervals where we are either increasing or decreasing. Okay? So to the left of B, we are decreasing. And that means that F prime is what? We're decreasing.
Negative.
It's negative. Okay? Then from B up to D, it's increasing. So what do we know about F prime between B and D? It's positive. And then from D over to positive infinity, F prime is negative again. Okay? So now as we look over here at the first derivative, what's the first derivative at A?
Negative.
Negative. And at C? Positive. At E? Negative. Okay? And then finally, we have our function. Now when we're talking about our function being positive, negative, or 0, we're looking at its location. Above, below, or on the x-axis. Alright? So A, the function is positive. B, the function is negative. At C, the function is positive. D, the function is, and E, the function is 0. Yeah, there we go. Okay? Alright, so now we're to B and C here. Describe the turning points. Now the turning points, when you hear turning points, what should you be thinking? Stationary points. Okay. Turning is motion, right? So we're looking at our stationary points, because that's going to show us where we're turning from down to up or from up to down. In other words, where we have a max or a min. So what's one of our stationary points or turning points?
B.
Alright, B. And B is a what? How would we describe that?
Minimum.
It's a local min, yep. Local or relative, you could say. Minimum point. Okay?
And that's all you have to do?
That's all you gotta say, yeah. Now notice here, relative or local min is important, because notice on the right hand side the function continues down to negative infinity. Okay, so it's not a global min, but it is a local minimum point. It's a change in direction. Okay? What's the other turning point here?
D.
D. Yeah, D. D is a...
Local maximum.
It's a local max. Okay? Alright, and then it says describe the inflection point. Okay. What is the inflection point?
It's
C.
C.
Yeah, it's C. That's kind of nice. They actually gave us that one. Alright. C. And again, that's because it was told to us. But that C is where F changes from concave up, since they asked us to describe it, concave up to concave down.
Mr. Nixon, I have a question. Do we always have to say local max or local min?
No, you don't. You
So
don't.
we
Typically,
just say-
anytime where we just say, if we just say max or just say min, typically we're talking about
Oh,
local
okay.
max and mins. That's much more commonly used than the global would be.
So is the same thing, global and local?
No. Global is over the whole function, and in this case, notice on the left side it goes up forever to positive infinity. So the global max, if you will, would be positive infinity. But D gives us a local maximum. And a local maximum or local min is in that immediate area, it's the lowest point. And there's a change in direction there. So now I want to show us a second method for showing whether something is a max or a min point, or a plateau point, okay? And that is the second derivative test. Now you might remember we said that if you are told to show that something is a local max or a local min, then the first thing you needed to show was that the first derivative equaled 0 at that point. But then the second thing you needed to do was show one of two things. You could either use the first derivative test, which the first derivative test that said that if your first derivative changes from positive to negative, that means the function changes from increasing to decreasing, so you have a local max. And if it changed from negative to positive, your function was changing from decreasing to increasing, which means you had a local min. That was one way of doing it, okay? The other way, which I told you about but we didn't know how to do yet, was the second derivative test. This is particularly helpful when you just don't feel like doing a sign diagram, or maybe you haven't found all of the stationary points, okay? And you don't feel like finding the rest of the stationary points, okay? If you can take the second derivative, then you only need the one stationary point that you're looking at in order to tell if it's a relative min or a relative max. And it all goes back to concavity, okay? So to prove whether a critical point, notice we're starting with a critical point, so we already know that the first derivative equals 0 here. To prove whether a critical point is a min or a max point, or a point of inflection, which would also make it a plateau point, if the first derivative at c equals 0, then x of c gives us a relative maximum if f double prime of c is less than 0. It gives us a relative minimum if f double prime of c is greater than 0. And it gives us a point of inflection if f double prime of c equals 0. Now, let's use words a little bit here. If this is true, if the second derivative is 0, we know the function is,
And it's a point of inflection. If it is 0?
no, if it's less than 0,
Original function?
Concave down.
it's concave down, okay? So, in other words, if we can show that the function is concave down at a critical point, we know it's a max point. if we can show that it is concave up at a critical point, we just proved that it is a minimum point. Okay?
This is like the lazy way.
It's a little bit easier, especially when all we care about is, like in this case here, we don't care about any other critical points that might exist. All we care about is negative 7/5. Okay? So, here we have the first derivative is 5x cubed plus 7x squared minus 5x minus 7. Show that there is a local min point. Notice here, I don't even know what the original function is. I can kind of think about it a little bit and say, okay, it's a polynomial, so if I took the derivative, I lost a power. So it was probably a quartic function. But I don't have it, and I don't have any way of knowing at this point what any other critical values would be. But what I can do is I can find the second derivative, make that 15x squared plus 14x minus 5, and then I can plug in negative 7/5. Okay, so that's going to be 15 times 49/25 plus 14 times a negative 7/5 minus 5. Okay? So let's see what I can do with this. The 15 and 25 will cancel out a 5. So that's going to be 3 times 49, which is 147 over 5. Minus 14 times 7 is 98. So that's a minus 98/5. Minus 5. Well, 5 is 25/5. And 147 minus 98 is going to be 49. 49 minus 25 is positive. Okay? No, it's 24. But really all we care about is the sign. So that is greater than 0. So that means that F is concave which way here? It's concave up. Which means that there is a local minimum. That's right. Okay? So there is a local minimum point at x equals negative 7/5. So you can see here, could we have used this negative 7/5, done some synthetic division to make this, to factor this out? And then we would have had a quadratic that we could have found the other critical points for. Yeah, we could have. Do I want to do that if I don't have to? No. Taking the second derivative and plugging it in is a whole lot easier. Okay? So it's not that we can't do it with the first derivative test, it's just, it'd be a pain to do it with the first derivative test. Now, I guess you could probably be pretty confident, even using the first derivative test, if you set up a sign diagram, and let's see, negative 7/5 is negative 1.4. So maybe if on your sign diagram you checked the increasing and decreasing at like negative 1.39 and negative 1.41, get super, super close on either side, and see if the change in direction. You could do that and be pretty confident that the other critical values were not between the value you chose and that. But this is a guarantee. Okay? Okay, so I've given you a little bit of practice here some of this is just finding the second derivative, okay? But then, and notice the difference in notation here, the second derivative, instead of f double prime, we have d squared y over dx squared. We saw that notation before. And then we've got a few other problems that you can try here as well, okay? So, yeah, so that'll be it, okay? But let's take a little bit of time here. We can work on this, practice together.